Thanks for the short introduction about myself. Well, before I start with an introduction about myself, I would like to say hello to everyone who's taking part in this webinar and welcome to this first session of our Industrial Tech Day. First of all, I hope you all are safe wherever you are in these rather difficult circumstances across the globe. We all hope that in the coming years, we can do such tech days in real time, face to face with you all like we had been doing in the past. In this session, I would be talking about the basics of how power from AC mains is safely converted into usable energy for your end device. Um, Before we start with the presentation, a bit of introductory information about myself. My name is Pranjal Srivastava. I'm the field application engineer at KEMET, responsible for the geographic region of South Germany, Austria, and Switzerland. So basically this region that you see here in the map. I would just change it to a laser pointer here. I'm with KEMET for over 2 years now. And prior to joining KEMET, I have 4 years experience as an automotive hardware design and development engineer with some tier 1 and tier 2 suppliers. And I hold a master's degree in microsystems engineering from University of Freiburg, Germany. Well, the agenda for this session mainly includes EMI filtering. What are the different noise forms and what are the different ways to get rid of those noise forms, simultaneously ensuring that the main signal is not lost. So we start first with the basics of EMI noise through AC mains and what types of EMI noise do we expect. Then we move on to EMI filter circuitry, some basic elements like chokes, safety capacitors, and so on. And I would be also briefly talking about some of our standard EMI solutions that include these basic elements already in themselves for industrial applications. And we would also be spending a few slides on AC harmonic filtering and what makes them different from a usual X or Y capacitor. So let's have a look at the basic block diagram for AC mains power extraction. No matter what device you use at your homes or at your work, they all have this basic sequence of electronic blocks. The AC main signal is firstly cleaned, made noise-free, and then supplied to the AC-DC stage, which converts it into a smooth DC waveform to be processed further by subsequent stages. We have, of course, also solutions for the PFC stage, but chokes would be covered also in this session, and inductors for boost converters as well as DC link or buffer capacitors would be covered in the next session. So we would not really be dedicating a session to PFC here, but the focus for this presentation would really be mainly on this EMI plus AC line filtering part of your AC mains to your load impedance conversion electrical networks. I take here an example of a home dryer. What we expect is that when you plug in your home dryer into your AC mains network, then you get this perfect looking AC mains waveform, like what you see here on your screen. And then based on this signal, your load driver here, which is driving your dryer, can actually process this signal and can make your dryer work the way you expect it to work. And so there is no need for any EMI or AC line filtering, any additional circuitry, if you were really getting a perfect looking AC waveform like this. So we can avoid this part and we can go straight to your load driver circuitry. But as we all know, reality is very different from an ideal life. There are always distortions. There are always these high frequency transients. There are always these noise signals that are superimposed on your main signal, on your main AC main signal, because of which, in addition to your load driver circuitry, you also need this specialized EMI plus AC line filtering circuitry. And the basic reason why you need this circuitry, this protection circuitry, is to be able to reduce to increase the signal to noise ratio and to reduce the noise on this signal, so that this could be processed as expected by a load driver circuitry, so that it can drive your dryer effectively as you want it to be, as you want it to be driven. Um, to make end device, why EMI filtering is really needed. So before we move on to AC line filtering, we would first be discussing about EMI filtering. Why do we really need EMI filtering? Well, it is needed firstly to make the end device immune to high frequency transients coming from AC mains network, and also to make the AC mains network immune to high frequency transients coming back from device to AC mains. So not only is the filtering block preventing the inward flow of disturbances, but in many cases also prevents an outward flow of disturbances. So key term here is conducted emissions and conducted immunity, as this is more effective against conducted and not really radiated disturbances. Now, before we move on to passive components to design an EMI solution, it's necessary to understand the EMI noise types that are needed to be filtered out by these components. EMI noise amplitude against frequency could look similar to this blue curve that you see here on the left of your screens. So when you take your device and go to an EMI lab inside an anechoic chamber, for example, and then you measure your different EMI radiations or your EMI disturbances at different frequencies, you would see something like this blue curve here. And just having this information by yourself is in most cases not enough to be able to effectively design the EMI filter circuitry, because you really have to understand what is the noise type, what is the reason behind which you see this EMI blue curve or this EMI noise, that what you see here in the blue curve. So what you need to really do is sort of split this noise into its real constituent noise signals by using these special interference splitter devices. I mean, of course, if you already know from before what the noise source is, then brilliant. Then you don't need to use any of these special devices. But in case you really need to analyze what is the real source of noise that is coming into your signal, then then using such interference splitters really helps, because it really splits your noise into two most more most wide category most wide noise categories, which are the differential or asynchronous mode noise, or common mode noise, or synchronous mode noise. Because once you have then split it, or once you know what are the sources of your noise, and only then can you really be in a position to determine for yourself that how do you really solve this noise problem for yourself. For example, if we have a look at individually then at these signals, we split it into synchronous mode noise or asynchronous mode noise, or let's say common mode interference or differential mode interference. Then you know that, okay, for a common mode interference, you need a solution, a specialized solution like a common mode choke or a Y capacitor. And for asynchronous or differential mode noise, you need a differential mode choke or an X capacitor. And this is how really you can divide then your different parts on your circuit diagram, that which part is really solving which purpose, or which part and which component is really getting rid of what type of noise that you are supposed to encounter as you work or as your circuit works. This is how a typical two-stage EMI filter circuit looks like. Components denoted with a blue letter here are supposed to be eliminating your differential mode noise or asynchronous mode noise, and the components denoted with a red letter here are supposed to be filtering out your common mode noise or synchronous noise. And the reason why I say synchronous or asynchronous again and again, it's simply because a synchronous mode noise is affecting directly your ground plane or your chassis. And this is why this noise would then be synchronously distributed across all your line and neutral planes. And this is why this sort of noise is also called common mode noise, because it's really common to all the AC mains line signals that you have supplying your device. And asynchronous noise is then affecting individual lines or the neutral line. And this is the reason why this is called asynchronous mode noise. So typically when the AC signal comes in, you have an X capacitor followed by a choke, which is then followed by this network of X and Y capacitors and so on. So it is not just one circuit consisting of many chokes and capacitors. It is actually one circuit consisting of two basic filtering modules. One part is taking care of your synchronous mode noise. The other part is taking care of your asynchronous mode noise. And typically you have an X capacitor that precedes then, which is then followed by chokes and so on. Usually you would have a differential mode choke and a common mode choke separately. But if you see this figure, then I have actually included the differential mode behavior as well as the common mode behavior within a single choke. Now, how might that be the case? Because usually you would come across two different sorts of chokes. Well, this would be the first basic passive element that I would be addressing in this presentation today. because we have these special type of chokes called hybrid or dual mode chokes, which actually exhibit both behavior. They have the common mode behavior and they have a differential mode behavior. And before we move on to onto these dual mode or hybrid mode chokes, let's take a look a bit into the basic functionalities of a differential mode choke and a common mode choke. Now, how a differential mode choke works. A differential mode choke is nothing. You take a core material and then you you sort of wind this coil of wire all around this core material, and this itself is enough to actually give you your differential mode impedance. And 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 the way this works is, at high frequencies, wherever you actually want that high frequency to be filtered out to increase your signal to noise ratio, you what this core material does is that this changing electric field due to this at this high frequency, due to this changing electrical signal, creates then a magnetic field inside this core. So your electrical energy at those frequencies is converted into magnetic energy that then goes around this core. And this is how you effectively filter out that electrical signal, in first in the form of magnetic energy, which is then eventually dissipated in the form of heat. And this is how basically you get your differential mode impedance behavior. As opposed to that, a common mode choke has two coils instead of one. So if you have actually any asynchronous mode noise, which is which is going to the right and coming back to the left, then then this asynchronous mode noise or differential mode noise would actually be creating magnetic fields that are opposite in sense to each other. So they would actually cancel each other out. So such chokes would not really give you any differential mode behavior. However, if you have a synchronous mode noise, and we expect this synchronous mode noise to be propagated in the same direction as what you see here on the bottom right of your screen, then these two magnetic fields actually these two electrical noise signals actually create magnetic field, which then propagates in the same direction. They have the same sense to them. And this is why you can effectively, in this case, filter out your synchronous mode noise or your common mode noise. Now, how a dual mode choke works. What what special feature we have included in this sort of choke, which makes a dual mode choke behave differently from a usual common mode choke, is that we have included this additional magnetic nose inside a common mode choke. And what this ensures is that your outer core, which is effectively filtering out your common mode noise, is working in combination also to this internal path, which is also filtering out your differential mode noise. And this is how, using the same choke, you actually get two behaviors. You get a common mode behavior and you get a differential mode behavior. And how do we implement this in real time? Well, if you have a look at these chokes, for example, you have the main outer core, and then you have this magnetic nose, or this magnetic stray inductance path. So it is basically this stray inductance, which is in many cases maybe not a property you wish for. But if in fact you enhance the stray inductance, then what this ensures is that your differential mode inductance, that you also get a certain differential mode inductance from your choke. And with and and by using this, what you can do is, instead of having two chokes, you can use only one choke. So instead of having a differential plus a common mode choke, you can use just one dual mode choke, or you can reduce the stress on your differential mode choke. So instead of using a big differential mode choke, you could use a smaller size differential mode choke, because you could use some of the differential mode impedance also from this dual mode choke here. It's also very important to understand the fact that the differential mode inductance of such dual mode chokes is a small fraction of the total common mode inductance that you get out of this choke. So what this means is that if you really need a big differential mode impedance for a signal, then either you use a smaller size differential mode choke plus this dual mode choke, or maybe you can increase your DC link capacitance, which is also on the same line, or maybe also the capacitance of some other AC filter capacitor, or maybe even your X capacitor, which is also existing on the same line. So with with certain strategies, there are many good ways of how to make use of such dual mode chokes. We have, of course, many different core materials that we offer for our different chokes. Um, we have starting with our nickel zinc material, which is mainly meant for the FM frequency range. We have there different core materials for different magnetic permeabilities. Then we have, of course, the manganese zinc, which is meant for lower frequencies, for the AM frequency range with different magnetic permeabilities ranging right up to S18H, which has actually a magnetic permeability of 18,000 mu. The HT here basically means, or the T here stands for high temperature, and it's basically these choke materials which basically give the choke its desired behavior, because anyone can take any magnetic material and while and wire around that core material, which would give you the needed impedance. But it's really what core material around which you wind your wire. This is the core material that really makes a difference in most of the cases. And of course, on top of both these core materials sits like a crown this nanocrystalline material. By the looks of it, it looks like a brilliant material. It has a very high magnetic permeability. It has a very wide frequency range that it covers. So why is it that we have manganese zinc and nickel zinc at all? Why don't we just stick with nanocrystalline? Because it seems like it's solving all the problems. One reason is price, of course, as you would have also guessed. But the financial aspect of the things is not really at the point that we would be addressing a lot during our tech day today. So I would be focusing more on the technical aspect of things. And the main technical, you can say, disadvantage with what nanocrystalline gives to you is this hard saturation characteristic. So although you have you use less material to build the choke with same inductance, but it could mean that beyond a certain current level, for example, if we talk about this zone here, then actually you have much lower inductance value available to you because of the hard saturation characteristics. And this is something you really need to take care about, that these high permeability materials, for example, the nanocrystalline here or the S18H with 18,000 mu, they look to be very good. Of course, they are very good to use, but you need to really look deep into your application regarding what are your current requirements, and if it's really helping you in your design, the high magnetic permeability. And there could be maybe a case that lower magnetic permeability is cheaper for your design. So you save on cost and maybe also on space, depending on what really is the kind of current that you need for your application. Um, One more feature that we have in our choke, or sort of this construction feature in addition to our cores, to improve your high frequency behavior, are these sort of split windings or these divided windings. We all know that it's actually the stray capacitance of that exists between the coils, which kind of affects your high frequency response. So it is really, I mean, if somehow you can reduce this big lump of stray capacitance, and instead of one big capacitor, you have two capacitors in series, so you have a better high frequency response. And this is basically what we do with our split windings and with our divided windings, that with the use of the same core material, you can actually further enhance your high frequency response using such unique features of construction. So this has nothing really to do with core, like what we saw also with dual mode chokes, that it really nothing has to do with, it really has nothing to do with the core material, but it has more to do with the construction types and how we construct the choke. A short look at our different choke at our different choke offerings for industrial applications. We start first with small drives or low power applications, where our recommendation would really be the dual mode chokes, simply because you also get a little bit more differential inductance, which you can use for the rest of your application by reducing stress on your differential mode choke, as already discussed. We have, of course, two different ferrite manganese zinc materials that we offer in our standard chokes for currents right up till 3 amperes. And then if we move on to slightly higher power levels, then our recommendation would be more in the direction of these toroidal or S-core chokes, or maybe these high power toroidal chokes with materials with much higher magnetic permeability, like 18,000 mu, or maybe even the nano crystalline material. Yeah, I mean, you can read, of course, uh, we would be sharing the slides with you. You can read in more detail regarding the individual details. But this is just to show our capabilities with uh, with our standard parts. We have, if you see, for example, very high current rating that we already provide with our standard parts. But what is really special to us are also these custom designs, which we take also great pride in. We have our own research and development department in Japan, and also our own EMI lab facility in Japan. So it is really possible for us to look deeper into your application requirements and to really come back to you uh, with specific solutions for your EMI problems, which would be cost as well as place effective for your application. And this is also, and I mean, this does not take much time for our team in Japan to give you a quick response regarding an initial feasibility study, if really it is a feasible possibility for us or not, depending on what your EMI solutions are. So there are some very interesting choke offerings that we have for the market in general. Now we move on to capacitors and the role that capacitors play in EMI filtering. As opposed to chokes, which are really filtering out your noise, the X and Y capacitors are, yes, of course, filtering out noise, but their main functionality really is also the conduction of voltage transients, or these some high frequency, high voltage pulses that could be a result of maybe a lightning strike or something like that. And this is where this is the main functionality, and this is what really differentiates an EMI capacitor from a usual AC filter capacitor. We all know about what the difference between a class X and class Y capacitor is. I will not go much in detail into this, but we know class X is between line to line or line to neutral. Class Y is between line to ground. Um, and what happens if there is a failure of a class X capacitor? Well, worst case, there would be a fuse getting blown off, and if the fuse is defective, then you would have a risk of fire. But what happens if a class Y capacitor fails? Because this is something which is really more safety relevant. You have your Y capacitor connected straight to ground or chassis. So what this means is if there is a short, let's say, that happens across the Y capacitor, then your entire ground level of your housing gets to that potential, which could be really catastrophic. I mean, which could have catastrophic consequences. And this is the main reason why actually the Y capacitors have a much more stringent safety requirements to fulfill. These are the requirements as specified by the IEC 60384 -14 norm. We see that for X1 and X2, the requirements are not as much. I mean, you have to, of course, ensure that your capacitor can withstand this standard pulse defined by the IEC norm. The duration of the pulse remains constant, but it's really the peak voltage that makes a difference, that if your capacitor is an X-rated capacitor or a Y-rated capacitor. And depending on what is the amplitude of this peak that your capacitor can withstand, we can certify or categorize your capacitors into Y2, Y1, or X2 or X1. Of course, this is just one of the main criteria. There are many other criteria that need to be fulfilled before we declare a capacitor as a safety capacitor. But this is really just to show to you that why a Y capacitor, or how a Y capacitor is more robust than an X capacitor. Now moving on to our film capacitor offerings for X and Y capacitors. With film capacitors in general, we have had some very interesting updates in the last few months, especially when we talk about our polypropylene-based film capacitors. Polypropylene, from its material, has many advantages, like it has a low dissipation factor. It has this self-healing effect, which makes it the safest technology to use. It has a low leakage current, and the list goes on. But it has two slight disadvantages. First disadvantage is its behavior at high temperatures. The second disadvantage is also it's a little sensitive to moisture. And this has been a bottleneck in the designs of many engineers, that how to use a polypropylene capacitor if you really need high temperatures and more sensitivity to moisture. And this has been the bottleneck that our R&D for film capacitors has tried to address in the last few months. And we have come up with many interesting updates, not just with safety capacitors, but also with DC link capacitors, which my colleagues would be explaining to you in the next sessions. But sticking to the polypropylene-based film capacitors, safety capacitors, we have here our R41T. The T here stands for high temperature capability, which means that we have now capacitors available for an operating temperature up to 125 degrees Celsius, and they are Y2 X1 rated, and they're also very robust. So it means 1000 hours, 85 degrees Celsius, 85% relative humidity, which basically means temperature humidity bias grade 3. So whenever you have requirements for a slightly higher temperature in your application, you need a Y2 capacitor, and this is for sure good capacitor to consider. The F862 V054. F862 series has been around for a while now, so this is not really a new series. This has been our standard offering for a robust X2 capacitor series. We have, however, come up with this new C spec, which we say as V054, and V054 basically stands for non-halogen free. So we offer this robust X2 capacitor series as halogen free as well as non-halogen free. Of course, you save on costs if you go for a non-halogen free variant. And this is again 85, 85, 500 hours specified. So not really grade 3B, but more or less grade 2B of the temperature humidity bias specifications. One very interesting update is really this R52P polypropylene based X2 capacitor series, simply because of the high CV value that it gives you. So it is not just a robust capacitor that addresses your high temperature, high humidity requirements, but it also packs in much more capacitance than what we are used to, not just from KEMET, but also if you compare on the market. I mean, there are some capacitance values that this capacitor offers, which really is which is based on a very small box size. You would not find smaller box sizes than those for those capacitance values. So in my opinion, this is really a series to watch, to look out for your future designs. If you need to space save and you still need a robust capacitor performing at high temperature, high humidity together. And this is also, of course, automotive qualified, just in case that is also relevant for your application. So in my opinion, this is really a very good series to consider for space savings and as well as high performance. Um, we have this new SMD SMP253 paper-based series. The main advantage that a paper-based series offers you is the high dB by dt capability, and now we also make it possible for you to use this in an SMD format, because the SMD construction type is something that also many designers really want for the future designs. So this is, if you have a requirement for a Y2 SMD capacitor series, then this is really a capacitor series to look forward to, the SMP253. And of course, I say look forward to, but these series have already been released. They're out there with the iRunner distributors. So go ahead, order your parts. If you have any questions, feel free to come back to us. In addition to our film safety capacitor series, we have also our ceramic conventional disc safety capacitor series, addressing different safety grades, addressing different voltages. We have, of course, also our Y1 rated ceramic safety capacitor series. And these series have been around for some time now. But I think the more interesting update here really is our new SMD Y2X1 rated safety capacitor series, which we offer in X7R as well as C0G. So especially if you have any requirements for a capacitive voltage divider circuitry where you also need a safety rating for your capacitor. So C0G is of course a good technology for that because of the low losses, low dissipation factor, and also the stability of that the capacitor offers you. So if you need to save further space to avoid the THT part, use an SMD part, then for sure we have some interesting offerings that we can offer from our SMD ceramic safety capacitor series. Moving on to AC harmonic filtering. The reason why I included a couple of slides on this topic in this presentation mainly is because we have seen many customers or many engineers are using an X or Y rated capacitor series also for AC harmonic filtering. Well, the purpose of an X or Y capacitor is much different from that of an AC harmonic filter. An X or Y capacitor is supposed to really conduct your high frequency voltage transients or your high voltage transients to ground. And not it's not really supposed to have a very high ripple current capability. Whereas if we talk about AC harmonic filtering, then the harmonics are defined as positive integer multiples of fundamental frequency, which means we are not really talking about as high frequencies as you would be talking about with X or Y capacitors. So we're really talking about much lower frequencies here. And the noise can be voltage or current, which really means that the ripple current capability of such capacitors becomes crucial. And ripple current capability of X or Y capacitors is usually not that high. And this is why we have special dedicated series for such AC harmonic filtering. The current harmonics could be they could be there due to nonlinear loads such as variable speed drives, and when these nonlinear loads then interact with your source impedance, then you have voltage harmonics because of that. And because of this, you need then special series for filtering out such AC harmonic noises. Uh, our standard offerings in this segment from our film capacitors are the box type, which is also our focus segment for automotive. And because it's focused for automotive, what this means is that this is a very robust series. It is it's again specified with an operating temperature of up to 125 degrees Celsius and has a very high temperature humidity bias. So it's also supposed to operate for 1000 hours at 85 relative humidity temperature. What this means is that this is really a very robust series, and this is why there are many focused markets which would really which we aim to target with this particular series. The CAN type series is more meant for large energy applications like a UPS system, renewable energy, and so on, simply because of the high voltage rating and also the high capacitance that they offer. They come with a safety overpressure device. They are UL 810 certified. So really for your high energy applications where failure might lead to some catastrophic consequences, and for such cases, this big CAN type film capacitor series is something that you could consider. Last but not the least, our standard offerings for EMI filtering for industrial applications, especially, we have solutions here for 3-phase as well as 1-phase. Of course, there are some competitors of ours as well who offer this series, but the big advantage that we have here is really we use our own EMI filter basic elements like chokes and capacitors. So what this enables, so what this I mean, the big advantage that this gives to us really is that we could be cost competitive because we use our own materials, and because we have a complete control of the process right from the basic elements till the final device. We can really look more specifically into your EMI requirements and therefore offer you an EMI solution just in case the standard solution is not there. But we have, of course, also standard solutions for a 3-phase EMI filter, for a single phase EMI filter. You can have a look at that. At the details on your own when we share the slide. But the idea behind this is really just to showcase to you our capabilities, that we don't only just offer basic EMI filter elements, but we also offer complete solutions in case this is what your requirement is. And this would be then the end of my presentation. Slightly above time, but I hope this was informative enough. So if you have any questions, please feel free to ask them right now.
Thank you, Pranjal. It was very interesting for me. I'm hoping as well for the attendees. Uh, according to the questions, I think